Hi, my name is Mike Idacavage, and the title of today's presentation is AOMA monomer, offering high T sub G and flexibility with low viscosity. AOMA is a trademark name for methyl 2-allyloxy methyl acrylate. This remarkably interesting monomer offers high T sub G and flexibility while having low viscosity. When I was reviewing the data several months ago in order to prepare this presentation, the words unique and versatile jumped out at me. I believe these two words describe AOMA quite well, and I expect that you will agree by the end of this presentation. To make my case, here's the agenda for today's talk. And here's the highlights for today's talk. I'll first introduce AOMA, its structure, and its basic polymerization reaction, and then move on to some of the properties that AOMA brings to formulations. I'll be covering its use as a diluent, its toughness, adhesion properties, thermal resistance, and finally water resistance. I'd like to then move on to future developments on AOMA and its class of materials, and finally end up with a summary. On slide 3, we see the basic AOMA structure. It's a relatively small molecule, and 2 points I like to make in that even though it's small, it really carries a big punch, because we have, as you can see, 2 areas or structures, functionality that it can react at. You have a terminal group, double bond group, and also the methacrylate functionality. And it's that combination that gives AOMA its unique properties. And here are the properties of AOMA itself. For the most part, they're exactly what you'd expect from a small molecule, but the one that is quite significant is its very low viscosity. So the viscosity at 25 degrees C is 1.57 centipoi. So it is extremely low viscosity, and this is why it acts as a very exceptionally effective diluent. Other than that, its properties are as you'd expect from a small molecule. And here's the polymerization reaction of AOMA. As I mentioned, it had the methacrylate type functionality, so it will react with a free radical as you'd expect for UV-curable or any free radical photopolymerizations. So in this case, in the upper left-hand side, I have a diagram of the AOMA structure, and it reacts with a free radical as you'd expect. This free radical then can undergo several different side reactions. You would normally expect it to have an intermolecular reaction and form a long chain, but in the case of AOMA, because of the structure properties, it undergoes an internal cyclization almost entirely, so usually greater than 95% cyclizes, and you get the tetrahydrofuran structure you see on the bottom right hand part of the slide. There are 2 points here that I like to make, or 2 parts of the structure I like to point out. You have the THF type structure there, highlighted in green, and the alkyl structure in more of a pink color. It is those 2 different structures in the polymer that give it both the combination of rigid and flexible properties. Here we see the reaction on the top end of this slide here, just similar to what we saw on the previous slide, but cutting out any of the side reactions. So we have your AOMA undergoing a radical cyclopolymerization, and you form this polymer chain that is composed of the tetrahydrofuran structure and the alkyl structure, giving it your rigid and flexible parts. For the monomer, again, its properties, as I mentioned earlier, you have very low viscosity, you have reduced oxygen inhibition, you're able to copolymerize with other methacrylates or acrylates, and you can make a wide variety of derivatives out of this basic structure. For the photopolymer, some of the properties it exhibits is very good heat resistance, mechanical toughness, it can be strong and ductile, and it improves adhesion to various substances. I'll be illustrating these further on in my talk with data to support that. Okay, how does does the reactivity of AOMA compare to with acrylates and methacrylates, materials that we commonly use in UV-curable formulations? AOMA reacts similarly to an acrylate. And we see here on the left-hand chart at the bottom, we have a heat flow on the y-axis and a time on the x-axis. The acrylate is in green, AOMA is in red, and methacrylate is in blue. And we see here with 3 parts per 100 of photoinitiator used to react the material, we have AOMA performing speed of reactivity very similar to the typical acrylate. And with methacrylate, as you'd expect, is quite slow and takes considerably longer time to react. Now, when you cut down the amount of photoinitiator used from 3 parts per 100 to half a part per 100, you stretch things out, you slow down the reaction, and the AOMA now is starting to differentiate itself from the acrylate, so it's a little bit slower, still at a reasonable speed though, and methacrylate does not react at all. So in general, AOMA can be thought of as reactivity speed similar to a typical acrylate. Now that's good data to have in the lab, so that was tested on an instrument, but how does it perform in a real world experiment? We see here we set up a very simple test. We have a tack-free, here's our tack-free test here. We start with our monomer composition. We coat a thin film using a wire round bar to give us a liquid film. This is then irradiated and then simply checked with a tack check, basically touching that surface with your finger until there's no tack found. On the bottom graph, we have a list of monomers that we tested. We have AOMA at the top using 2 different cross-linkers, red DPHA, and the light gray is a urethane acrylate, diacrylate, and then we have AOMA compared to common monomers such as THFA, PEA, IBOA, NVP, and so forth. And we can see that AOMA reacts quite rapidly. I'd like to note that these conditions are in air, so it's not an oxygen-free atmosphere, so you would expect to get some oxygen inhibition. And AOMA reacts quite rapidly in the presence of oxygen. Now, how does AOMA serve as a diluent? I mentioned early on that because of its low viscosity, it could serve as a very good diluent, which is why monomers are commonly used in our formulations. The chart that you see, the graph that you see at the top, with viscosity on the left-hand side and ligament content on the x-axis, is made from the data that's shown in the table below it. So these are the exact same. It's the exact same experiment. The oligomer, by the way, is an aliphatic urethane diacrylate. And we see TMPTA, so a very common monomer that we use, while starts out extremely low, as you start going up to, say, 30% or 50% oligomer, the viscosity starts to shoot up quite high. THFA and IBOA are quite a bit more effective. But AOMA is probably the best diluent of these combinations. We see the data below on the table, and you can see that we're, and we'll again, I'll look at the 2 extremes here. For TMPTA, you start at around 94 millipascals or centipoise. It quickly goes up to close to 6,000 centipoise. using the same amount ratio of AOMA to the oligomer. We started at 2. And by the time you hit 50, you're only at 114 centipoise. So it stays very low. So this becomes a very good and effective monomer to dilute high viscosity oligomers. Here's an experiment we did where we compared the use of AOMA to IBOA in a formulation. We used for monofunctional monomers AOMA and again IBOA. We have a difunctional monomer for cross-linking HDDA and a urethane acrylate. In the column at the right at the end we have 30% IBOA, 20% HDDA, and about 50% of the urethane acrylate. On the left of that, in the first column, we eliminated the IBOA, but we added 20 parts of AOMA. Still kept the HDDA the same, and we upped the amount of urethane acrylate. So what we did was increase the amount of the effective oligomer and lowered the overall amount of the monomer. And then when we compare those properties, viscosity is a little bit lower for the AOMA, as you'd expect with the effectiveness of the AOMA as a diluent, but our tensile strength went up, and along with the tensile modulus. Elongation stayed roughly about the same, and HDT also stayed about the same. And we'd expect these results. This is what we'd want. By dropping down the viscosity a little bit, we're able to add more oligomer to give you the strength and modulus properties we wanted, and that's shown in this experiment. But what would happen if on this slide we see a typical starting point formulation for a polycarbonate coating. In this case, in our control is using IBOA, and we replace the IBOA with AOMA. So the first column on the left is our control experiment using IBOA, where we have 45 parts of a hexafunctional aliphatic urethane acrylate, and then TMPTA and IBOA as comonomers, and a photoinitiator. In our experiment, we used AOMA instead of IBOA, so we only needed to use a little over 9 parts of AOMA, and we achieved the almost identical viscosity, so 510 centipoise for IBOA, 503 for AOMA. Now if we look at the properties we get out, so we now have the same viscosity used for the application method that we needed, and the pencil hardness went down a little bit, but the scratch resistance went from moderate scratches to no scratches. Adhesion improved, and solvent resistance improved from slight whitening or hazing from the solvent to no change. So we were able to get a better performing coating, polycarbonate coating, when we moved from AOMA, from IBOA to AOMA, and keeping the viscosity at the same level. Okay, how about toughness? How does AOMA affect the toughness of your coating property? On this graph, we see on the y-axis is T sub G, and on the x-axis is the mandrel diameter, or it's as you bend your coating around a mandrel or roll, it indicates how flexible your coating is, or your photopolymer is. So we selected a few typical monomers. So we have IBOA up in the upper left, going down through DCPEA, and then THFA. So we go from a very brittle photopolymer down to a very flexible photopolymer as you cure the material. AOMA is a real outlier here. In this case, you're able to get a very tough photopolymer using AOMA, yet it's still very flexible. So it really combines the best of both worlds. And again, that's due to that the tetrahydrofuran ring structure to give the toughness, and the flexibility coming from the alkyl chain. So the use of AOMA can improve your toughness, but still retain some flexibility in your final formulation. Another area we wanted to look at was how does AOMA affect adhesion? In this case, we used a very common adhesion test, crosshatch test, where we cured a film on a substrate. We then cross-cut it, made our crosshatches, 10 by 10 pieces, applied adhesion tape over it, and then peeled the adhesion tape, and then we counted the remaining pieces that are on the board. So a very common way of looking at adhesion. And I'd like to share with you the results now on this slide. So this is adhesion to plastics. And we have on the left-hand side, the first column, a range of very common plastics: PMMA, polycarbonate, PC, ABS, PET, EVA, and so forth. So we have a range of plastics there. And on the top row, we have the range of monomers we looked at. So AOMA, it's highlighted in blue there. It's on the first column. Then THFA, CHA, IBOA, NVP, and so forth. And we see while for plastics, AOMA is one of the better ones that we have available here when measuring 100% in plastics. For COP and EVA, it falls down a little bit, but other than THFA, which really was quite good for all of them except COP, most of the other monomers tend to have fair to poor adhesion. Moving from plastics to other substrates, again we have the other substrates: glass, aluminum, copper, silicone wafer. On the first column there, and across the top we have our list of monomers that we looked at. And in this case, AOMA is definitely one of the better monomers when it comes to adhesion. In fact, in pretty much all cases, it's 50 or greater, with majority of them being in the upper end, such as for copper. And it's interesting because you come to, say, silicone wafer, one of the toughest substrates to get adhesion to, while this I would call is fair to good. All the other monomers we tested, THFA, CHA, IBOA, were not effective at all. So in general, AOMA is one of the better monomers when it comes to adhesion. We were interested in understanding why that occurs. So on this side, we ran a DFT calculation of AOMA pentamer. So we took a look at that, looked at its surface charge distribution, and we saw that it's very well balanced. So you have this very evenly balanced surface charge, and we believe this is the reason why AOMA in the homopolymer is such a good, has such good adhesion properties. Moving on from adhesion to thermal resistance, on this slide we compare THFMA, so the homopolymer of THFMA, with MMA and AOMA combination. So the way this experiment was run is that we made our homopolymer of each of the test materials, and then dry that material, and then heat it up on a TGA, using dynamic TGA under nitrogen, and watched at what temperature it would decompose at. So for THFMA, something which has a somewhat similar structure you expect to AOMA polymer, we have that material starting to degrade at around 250 centigrade. Let's compare that with MMA, so that's in the green line here. That is quite stable, and it starts to degrade somewhere above 300, perhaps around 350 or so. Then we started doing various combinations of AOMA and MMA. So the yellow is a 30-70 AOMA MMA combination, then 60-40, and finally 100%, so pure AOMA. And we could see that as you increase the amount of AOMA, your polymer becomes increasingly resistant to thermal heatings. Now we've looked at AOMA in a variety of different experiments to see how it can improve the properties of various formulations. We also wanted to see what effect it had on water absorption. So we used TMPTA as a cross-linker and evaluated a range of monomers with AOMA being on the left. In this case, AOMA was just average. It did not really have any exceptional properties in improving water absorption. And looking at the structure with the tetrahydrofuran ring, the oxygen species, I guess it is not that big of a surprise that it has pretty high water absorption in its formulation. So I would just list this as fair in this case. So where do we go from the basic AOMA structure? I wanted to end this presentation by showing you some of the future developments that are being done on that structure. So AOMA can be thought is a monofunctional material. You are able to functionalize that structure and make it into a difunctional, trifunctional, and so forth. So you can expand basically AOMA monomer class through derivatives. Let's see, what does that mean? And here's an illustration of AOMA derivatives that are currently under development. You can really make a large and wide range of structures using the basic AOMA structure. We have, of course, a monofunctional, where you could add, say, a cyclohexyl group on, or a benzyl group. You can make it difunctional, as you can see in that middle column there, various molecules that have been made. You can also go from difunctional to trifunctional. On the top, we have hexafunctional there on the bottom right. So becomes really a versatile starting block for making a wide range of materials. What we expect from these in general as a class, some common performance properties. It should be maintain its curability under air because it still has that cyclic THF type structure. Once it's cured, you get the toughness, heat resistance, adhesion properties. All of those hopefully should be maintained. On this slide, you see a listing of the properties of various AOMA derivatives that have been made. On the top left, or the first column, you have our basic AOMA structure, and then going across you have the cyclohexyl, a TPG type structure, and a TMPTA type structure. We see then going down, if you look at some of the properties that we have, the reactivity improves quite a bit on going from AOMA to the cyclohexyl, TPG, and TMPTA, especially as you go to the highly more functional materials, because you have, just as you see when you go from difunctional to trifunctional materials with other monomers. The viscosity does increase. You're increasing the molecular weight of your structure, but it doesn't really increase too dramatically. The vapor pressure improves as you increase the size, and that's very helpful because it reduces any odor you may get. And the shrinkage also improves on going from AOMA to the various functional materials. So what we see is our basic thought premise was that as you functionalize this materials, you're going to see improved properties on the homopolymer of the AOMA structure. What you get, fortunately, as you increase the molecular weight with AOMA going to derivatives, you don't get that large of an increase in its viscosity. So it still maintains its very good diluent properties. On this chart, we have a comparison between a range of acrylates, so that's in green, range of methacrylates in blue, and a range of AOMA derivatives that we made in red. And while they all increase as you increase the molecular weight, the AOMA family tends to increase at a slower rate than when compared to the acrylates and methacrylates. So that's very helpful. You can switch to a derivative of AOMA and still get some of the very good diluent properties that you'd want to achieve. How are the mechanical properties as you go to the higher molecular weight derivatives? Here's a comparison between a TMPTA-like AOMA derivative called in the lab FXAOMA TMPTA and TMPTA itself. So we have viscosity, it's lower in viscosity. The elasticity is close to the same. The Fmax, or the maximum stress or force before failure, is improved. You have an improvement in the elongation and improvement in the toughness. So going to a very similar structure, but now based on AOMA, you're seeing an improvement in the viscosity and a corresponding improvement in the overall mechanical properties. And here's the results for tensile testing we did with against cyclohexyl, benzyl, NPG, and TMPTA type functionality across the top. We see as we go across from left to right, we get good elasticity properties, so it maintains those. The force max, or Fmax, is still quite good. Elongation really improves with the benzyl. The other systems remain the same, and we get a very large increase in the toughness when we go to the benzyl functionality. So we do maintain the mechanical properties on the larger derivatives of AOMA. So I'd like to summarize what we've discussed here during this presentation. AOMA exhibits low viscosity, low oxygen inhibition, and good reactivity. The cured photopolymer has a high T sub G with good flexibility. Now, when compared to other monomers, AOMA can contribute to an improvement in the adhesion of a coating. And the AOMA basic structure can be modified to produce a wide range of derivatives. And early work on these derivatives indicates that they demonstrate improved properties while still maintaining low viscosity. So with that, I'd like to thank you for your attention. And if you would like to request more information on AOMA and its derivatives, I recommend that you contact Tony Franklin at tony.franklin@nagase-nam.com, and Tony will be glad to help you with your needs in regards to AOMA or its derivatives. So, thank you very much.